Physics Lab 2, presented and created by Andrea Otero. For experiment number 2, we had to choose an object and throw it from rest from a certain height in order to analyze the motion of a falling object. For this experiment, I chose an apple that had a mass of 120 grams, which is equal to 0.120 kilograms, and decided to throw the apple from a height of 2.05 meters in a closed environment in order to reduce air resistance, as the picture clearly illustrates. In this lab, we are also going to apply as a fundamental principle Newton's second law, which states that the final velocity is equal to the initial velocity plus the force acting on the system times the change in time divided the mass of the object. In this experiment, however, there will be a net force acting on the system, in this case on the apple. As the video shows, the motion of the falling object was analyzed through tracker by plotting the position of the apple for a certain time interval in order to create a position versus time graph as the one shown to the right. Here is a clearer picture of the plot and the y values and the time values. Based on the data extracted from tracker and the experimental video, a first computational model was used using Python. In the model, the initial conditions were plugged in, such as the mass of the apple, which was 0.120 kilograms, its initial velocity, and initial position, which were both vectors of 0, 0, 0, since the object was dropped from rest, and a delta t of 0.006 seconds was chosen. The constant g was determined and defined as 9.8 meters per second squared, and j hat was also determined in order to specify the unit vector. The constant b was equal to 0, because for our first model, the drag force was ignored. Additionally, the interactions acting on the system were added to the code. For our first model, the force net acting on the system was chosen to be determined only by the weight of the object, the gravitational force. Here we can see a video of our first model running, representing the motion of the falling apple. A second computational model using Python as well was constructed in order to represent the motion of the falling apple as well. This model had the same initial conditions as the first model, as we can see on the code, the same mass and the same initial velocity and position. The first change made to the code, highlighted in yellow in the image shown, was that a value for b was determined. After experimenting with various possible values, finally the value that gave the base approximation for the model was a value of b equals 0.008. Since the drag force was taken into account, such had to be modified into the while loop, where the net force was now going to be equal to the weight, or gravitational force, plus the drag force, calculated using the value of b, and proportional to the speed squared of the falling apple. Finally, arrows were arranged in the code in order for them to appear. The magnitude of the arrow scale was determined by the weight and the height. As the running model shows, the blue arrow representing the drag force was really small, because due to the object chosen, the apple, and to the environmental factors where it was dropped, the drag force, meaning the air resistance, was almost negligible. Using Google Spreadsheets, a position versus time graph was created which compared the experimental model and the two computational models constructed in Python. By observing the graph, one can conclude that both models were really similar between each other and with the experimental model. This is due to the characteristics of the apple and to the environment where the apple was dropped, since the air force, or the drag force, became almost negligible. Examining the velocity versus time predicted by my models with and without drag force, I concluded that neither of them really had terminal velocity, because such would imply that the sum of the drag force would be equal to the downward force of gravity acting on the object. Since the first model did not take into account the drag force, not much can be said about it, and since the drag force was almost negligible, the only point where they were both equal to 0 is at the end. The second discussion question addresses the question what would have happened if the object had an initial velocity. Only by observing Newton's second law we can see how having an initial velocity greatly affects the final velocity, giving it a greater magnitude. By observing the models and the graphs, one can also conclude that such would affect the drag force, since it is proportional to the square of the speed.